We're going to look back at all the transformations we've done so far, translations, reflections, and rotations. We're going to look specifically at the rules for the coordinates. If you do one of those transformations, what happens to the coordinates? And so we're going to look at those. They're going to be called algebraic representations because they're going to be shown to us at first as if we could use any coordinates for them. So for example, translations is where we're going to start. It says the rules shown in the table describe how coordinates change when a figure is translated up, down, right, and left on the coordinate plane. And we've talked about this a little bit already, but just take a look here at this box and let's see if we can make sense of what's going on here. So if we go right a certain number of units, we're going to add, remember right would be an increase with x, right? So we're going to add whatever that amount is. So if we go right 2 units, for example, we'd add 2 to the x coordinate. So to write that rule, we'd show our original coordinates as just any x value and any y value, and show that we would add whatever amount a was. In this case, we gave the example of 2 to x. So if this was 3, we would add 2 to that, and it would now be 5. So this is just a way to show the rule for what that would be. If we move left, we're going to be subtracting a certain amount from x, right? If we're moving up a certain number of units, then we're adding a certain amount to y. If we're moving down a certain number of units, we're going to be subtracting that amount from y. And I'm sorry that these copies didn't come up real well, but this is supposed to be subtract a certain amount from y. So, algebra doesn't give us specific numbers. It's supposed to be something we can use to plug in for anything. So that's why they don't use specific numbers. But here's an example of what they're talking about here. It says triangle XYZ has vertices at 0, 0, 2, 3, and 4, negative 1. Find the vertices of the triangle x prime, y prime, z prime after a translation 3 units to the right and 1 unit down. Then graph the triangle and its image. So we've done this with translations already. So this isn't anything brand new necessarily. You have your original coordinates here. And it shows, if we're going to be translating to the right, 3 units to the right and 1 unit down, we're going to be adding 3 to each of the x coordinates and subtracting 1 from each of the y coordinates. And so it shows you the result of that after you do that. So 0, 0 would turn to 3, negative 1. 2, 3 would change to 5, 2. And 4, negative 1 would change to 7, negative 2. If you increase all the x coordinates by 3 and all the y coordinates, you subtract 1. So here's what that would look like. And you can see, here's the original triangle here. And here's the new triangle after you've done a translation, 3 units right and 1 unit down. And each one of these is translated 3 units right and 1 unit down. So we like I said, we've actually done some translations like this where we've found the new coordinates. So let's go ahead and take a look at number 1 here of the practice. It says a rectangle has vertices at 0, 2, 0, 3, 3, negative 2, and 3, 3. What are the coordinates of the vertices of the image after a translation? And then it gives this algebraic rule. So we haven't seen it quite described like this before, but all this means is you have your original coordinates, and here's the change. We're subtracting 6 from x and subtracting 3 from y. So they want us to go ahead and change these coordinates so that they're like that. And then they want us to describe what the translation was. So what actually happened here as far as our movements. So if you can, go ahead and pause the video and see if you can figure out what those new coordinates would be. And then I'm going to do this right here, right now, in just a second and work this out. But I want you to see if you can come up with them on your own first. Alright, so for all of these here, let's go ahead and set these up. We're subtracting 6 from x, so 0 minus 6 would be negative 6. 0 minus 6 would be negative 6. 3 minus 6 is negative 3. And 3 minus 3 is negative 3. So far we've decreased all of our x coordinates by 3. Then we have this y minus 3, so all of our y coordinates are going to subtract 3. So negative 2 minus 3 is negative 5. 3 minus 3 is 0. Negative 2 minus 3 is negative 5. And 3 minus 3 is 0. So those would be the new coordinates. Now we're going to describe the translation. It is, and you got to think about if we subtract 6 from x, are we moving right or left? Are we moving left? So it's left 6 units. Okay, and then if we subtract 3 from y, are we moving up or down? We're moving down, so and down 3 units. So that's the actual direction and distance we would move, given that rule. Let's take a look at reflections real quick. That's on the back side of that page. And we've kind of talked about this one already too, so I'm going to try to make our way through this one pretty quick so we can get to rotations, so that's the one we haven't done yet. Algebraic representations of reflections. The signs of the coordinates of a figure change when the figure is reflected across the x-axis and y-axis. The table shows the rules for changing the signs of coordinates after reflection. So across the x-axis it says multiply each y-coordinate by -1. Well, what happens when you multiply something by -1? Like 5 times -1 is -5. -5 times -1 is +5. So in the end what ends up happening here is it just changes the sign of the y-coordinate. But you notice nothing happens to the x-coordinate, right? And we talked about this in class. If you reflect something across the x-axis, the x-coordinate will stay the same, see no change for x, but the y-coordinate will change to its opposite. If it has a positive, it changes to a negative. If you put another negative in front of a negative, it changes to a positive. Across the y-axis, multiply each x-coordinate by -1. So the y-coordinate will stay the same when you flip over the y-axis, but the x-coordinate changes to its opposite. So let's take a look at the example here. Rectangle RSTU has vertices at -4, -1, -1, -1, -1, -3, and -4, -3. Find the vertices of rectangle R prime S prime T prime U prime after reflection across the y-axis. Then graph the rectangle and its image. So here are the original coordinates. The rule in this case, if we're reflecting across the y-axis, is that the y-coordinates stay the same. So see no change with the y-coordinates, but the x-coordinates change to their opposite. So they're going to show that by multiplying by -1 for each one of these. So -1 times -4 is +4. And you can see that each one of these got changed to the opposite. And again, we've actually done that one in class before. So you can see here what that looks like. Here's your original coordinates. They graphed this one, and then they graphed this one. You can see that that's a reflection across the y-axis. Everything is the same distance from this line of reflection, S and S prime, R and R prime, and so on. So they're able to make that reflection. All right, this problem here says triangle ABC has vertices at A, -2, 6, B, 0, 5, and C, 3, -1. Find the vertices of triangle ABC after reflection across the x-axis. So I want you to go ahead and see if you can come up with those coordinates right now. Pause the video if you need to do that. And then I'm going to write them here. I could just set this up. A prime, B prime, and C prime. Well, we're reflecting across the x-axis, so the x-coordinates will all stay the same. So -2, 0, and 3. The y-coordinates will all change their opposites. So -6, -5, and -1. All right, let's get to this last one here, because this is the one I really want to spend some time on. This is algebraic representations of rotations. Now you'll notice that on the assignment that we did for rotations, we didn't talk about how the coordinates change. These rules are a little bit trickier, and I did not introduce them to you when we did rotations. We just tried to do rotations with the pieces of paper and by seeing where we're at on the x-axis and y-axis and kind of estimating where that would be when we rotated that. But there are actual rules for the coordinates that will help you make sure you get the exact rotation correct. So when points are rotated about the origin, the coordinates of the image can be found using the rules shown in the table. So if you do a 90-degree clockwise rotation, now I'm gonna disagree a little bit with the order here. It's still gonna have the same effect, but it says multiply each x-coordinate by -1, then switch the x and y coordinates. You can do that, but what I'm gonna have you guys do in class is go ahead and switch the coordinates first. So whatever you have for x and y, switch them, and then you're gonna change the one that is on the right. So I like that because it can help you remember with clockwise and counterclockwise. If you go ahead and switch them, and then you do the one that if you were to go clockwise, you would hit first if you start at the top, right? So you would kind of do the one that is on the right and switch that one. So I'll show you what I mean here in a minute. It'll make more sense. If you do a 90-degree counterclockwise rotation, you're still going to switch the x and y coordinates. You see that switch there. But then we're going to change the one that is on the left. the one that is now in the x coordinate spot. This one would be changed, the one that is in the y coordinate spot now. This one changed the one that is in the x coordinate spot to the opposite. If you do a 180 degree turn, you don't switch either x or y. All you do is just change both the x and y coordinates to their opposites. So the numbers still stay the same, the digits themselves, but you'll change to the opposites, and those will give you the new coordinates. So let's give this a try. And this is a little confusing when we just go over the rules, but let's see what this looks like if we actually get a chance to graph this and see this in practice here. So quadrilateral ABCD has vertices at -4, 2, -3, 4, 2, 3, and 0, 0. Find the vertices of quadrilateral A prime, B prime, C prime, D prime after a 90-degree clockwise rotation. Then graph the quadrilateral in its image. So, you know, they did their rule here. What I'd like you guys to do is just kind of ignore this, because I'm going to have you do it just a little bit differently. But in the end, we're going to see what we get. So here, you see A is -4, 2. We're going to switch those, so it would become 2, -4. But then with the 90-degree clockwise, we change the 1 on the right here to its opposite. So in the end, it's going to become 2, +4. Okay? For B to B prime, we're going to switch the 2. I want you guys to write these down with me here. The initial switch here. So we're going to switch it. It's going to become 4, -3, and then change the 1 on the right to its opposite. You can see we have 4, +3. Okay? For 2, 3, we're going to switch them. It's going to be 3, 2. But then we're going to change this 2 to the opposite, the one on the right to its opposite. So 3, -2. If you're at 0, 0, and you switch them, you're still at 0, 0, and then you change 0 to its opposite, it's still 0, right? Which basically just means anything on the center of rotation at the origin right there is still going to be in the same place when you do your rotation. So take a look, and I'm not going to dissect this too much here, but I just want you to see what happened with these. So take a look, for example, at A right here. This was the original A. It was at -4, 2. You did this 90-degree rotation, and it turned up at 2, 4. You see right there? And so all we did was we switched the 2 and then changed the 1 on the right to its opposite. And then we have B here at -3, 4. We switched the -3 and the 4 to 4, -3. And then we changed the 3 to a positive, so 4, 3. And it did that for all of those. And that's how you can graph that. And make sure you get those in the right spot without having to just guess, or without having to use a little piece of paper to make sure that you made a 90-degree angle and all that stuff. So there's actual rules for the coordinates. All right, let's do number 4 here. And it says a triangle has vertices at -2, -4, 1, 5, and 2, 2. What are the coordinates of the vertices of the image after the triangle is rotated 90 degrees counterclockwise? Now I want you to pause the video and see if you can come up with these coordinates on your own, and then I'll do it here and you can see if you got the right thing. So let's meet J prime, K prime, and L prime. So the first thing I'm going to do is I'm just going to switch the coordinates. So -2, -4 will change to -4, -2. And then if I'm going counterclockwise, I'm going against the way a clock moves, I'm going to change this one, the one in the X spot. So it's going to change from negative to positive. So you can either just erase that. That's probably preferable to changing it to a positive. Okay, K. It was 1, 5. We're going to change it to 5, 1. And then change the one that is on the left to the opposite. So it's become -5, 1. And then L prime, I'm going to switch the 2. They're both 2s. So still be 2, 2. And then change the 1 here to its opposite and become -2. So if we were to graph this triangle, the original coordinates, and then graph this one, it would make a 90-degree counterclockwise rotation. So that helps us, because counterclockwise is going this direction, so it helps us to remember which one we change. So I just like that better than changing it first and then switching it, but you really can do it either way. All right, we're going to talk more about this in class, especially these rotation rules, since this is new to us. But hopefully this gives you an idea of doing rotations maybe a more consistent, more accurate way.